Good morning. Oh, it's good to be back. I took a Monday off. I had to attend a meeting and just couldn't be scheduled any other time. Actually, you know what happened? It actually could be scheduled for another time. I got a note like half an hour before that meeting was going to start that it had been rescheduled to Tuesday. So, but by then I already made an announcement. I'd already posted up a video of basically the recording I made last semester. And so there we go. So hopefully you got a chance to watch that video. It was it's kind of like watch me do some image manipulations, like what do we do? Darken an image, lighten it, turn it black and white, reverse it. So, flip it end for end, not rotate it, but actually flip it. And, some other stuff. So hopefully you got something out of that. Can you all hear me today? Good. Sometimes I can't tell if I'm being heard. I hear myself in my headphones here, but I can't tell if I'm being heard. Well, somebody already said the topic for today, which is pointers, is probably the most important topic that you can learn in your programming life, it says. And maybe that's true. I mean, certainly it is one of the most important topics in a language like C, because you really can't get very far without using pointers. C++, Java, they have pointers as well, but they're hidden from you. There's no explicit syntax for dealing with memory addresses, but it's going on behind the scenes, and it is something that you should be aware of, because I've heard that this is one of the questions, or questions like this are ones that interviewers like to ask on technical interviews. Whether you know something about pointers and whether you can think more abstractly about where things live in memory versus just what their value is, like whether x has the value 10 or not. But where does x live, and can it be moved around? So today's topic is an introduction to pointers in C, and we'll be looking at pointers. We'll be using pointers for basically the rest of the semester. So if you don't get it, if you don't quote-unquote get it this week, or even over the next 2 weeks, I'd say don't worry, just keep exposing yourself to them, keep using them, and then hopefully things will start to click and you'll kind of understand what's going on. But we're going to introduce the syntax to you today and introduce some basic uses of pointers, and then like I said, hopefully it'll start to kind of like gel in your brain as time goes on. So before we begin, are there any questions that you have for me? Oh, got nothing? All right. Well, let's take a look at the program that we've been writing over the past couple of weeks. We've have this program where it builds an array, and it either fills it with some random values or just fills it with some fixed values. And then it does things like reverse them, rotate them, find the minimum, find the maximum, find the average, things like that. So let's take a look at that. Interesting, it's not switching over to my laptop input. So let me see what's going on there. I'm gonna have to lower my desk because I have to reach behind my monitor. See what's going on. Right now you got my head really big. But let's see what's going on here. Does this do anything? No? That one? Hey. Well, okay, those work. Let's try this again. There we go. Ah, that's what I wanted. I don't know why that didn't work, but there it goes. Desk is coming back up. I'm standing at my desk. I don't have a seated desk. The reason for that is the desk I'm standing at is like my everyday, you know, when I'm just doing work desk. And, you know, there's a camera here, there's lights up here, there's some monitors in front of me. And then when I'm just doing regular work, I don't want like all that stuff like, just, you know, staring at me in the face. So I have one of those desks that can go up and down. And so when I'm doing my class, it's up, and I'm looking at all the video equipment. And then when I'm just doing regular work, I bring the desk down and I sit at a chair, and then it's not all like cluttering up my vision. Okay, so just as a review, here's the program we've been writing. We have some various functions in here to deal with arrays, like one to print out an array, one to fill an array with random values, one to double all the elements of the array, so to multiply all the elements by 2. Find the maximum, find the sum of all the elements, find the average, rotate the elements, reverse the array, and shuffle the array. And then finally a main that just calls those various functions. So if we take a look at some of these functions like shuffle and reverse, maybe even rotate, let's go look at those. So here's shuffle, and the way shuffle works is it just loops through the length of the array times 3, so it does 3 times as many as there are elements of the array, iterations. It picks 2 random elements and then swaps them. And you do this a whole bunch of times, and you should get a nice shuffled up array. And then for reverse, it takes the outer 2 elements, swaps them, and then the next 2 on the inner, going towards the center, and swaps those. Next 2 going towards the center, and swaps those. And it keeps doing that until it reaches the center of the array. So both of those functions, reverse and shuffle, have internally this set of statements that will take 2 elements of the array and swap them. So essentially we've got the same code written twice. We take an array element and we put it into a temporary variable. Then we copy another array element into the one that we just moved away. And then we take the temporary and put it back into the second array element. So that's in reverse. And then in shuffle, we got the same thing going on. We take an array element, we put it in temporary, then we copy it into another one, and then we put the temporary back into the second array element. So we got a swap happening in both cases. And so, you know, as a good programmer, we should think we might want to write a function to do this for us. We might write a function called swap. And the whole purpose of swap is to take 2 numbers and just swap them. So let's go ahead and write swap. Let's put it up here. So swap is going to be void because it's not going to return anything. It's just simply going to take 2 numbers and then just reverse their positions. So I've got 2 numbers, A and B. And what I want to do is, like, let's say you're in shuffle. I'm just going to call swap. And inside of swap, I'm just going to put in the 2 array elements that I want to swap. So array I and array J. What I'm handing to swap are not actual like elements of the array. They're just numbers. So swap really has no idea where these numbers come from. In other words, I could, like in my program, just say, you know, like int x equals 5, int y equals 10, and then just say swap x and y, right? So that the value of x and the value of y get reversed. So the swap function should not know where these numbers come from. All it knows is that it gets 2 numbers that it needs to swap. And then same thing here in for reverse. I'm just going to call swap and pass in the 2 array elements that I want to swap, which is this one and this one. So that's what I want to do. I just want to call swap, hand it two numbers, and then it just reverses them. Okay, so inside swap, I need to make a temporary variable. Then I need to copy A into the temporary variable. And then copy B into A, or A into B. No, B into A. And then put the temporary variable back into B. So that's basically what swap does, is it takes one of the elements, puts it to a temporary, and then copies the other element into the first one, and then takes the temporary and puts it into the second one. But the problem is that this is not going to work. It'll compile, but we can see now that shuffle is no longer shuffling the elements because it looks just like the one above it. And reverse also is no longer reversing the elements because it's not actually swapping the elements. And so the problem here is that swap doesn't get the actual values, doesn't actually get the actual variables that we want to swap. What it gets is a copy of the values that we want to swap. So what goes into swap is not the actual element of the array. It's just a copy of what it found there in the array. So if it found the number 7 in the array, swap gets the number 7. And if it also found the number 12 in the array, swap gets the number 12. And it does internally reverse the 7 and 12, but we can what we'll see here shortly is that it doesn't actually reverse the elements themselves in the array. So let's put that into our visualizer. And let's just do something like inside the main, let's go int array. Let's put 5 elements into it. Let's go 9, 2, 1, 7, 3. And then I want to call swap of array element, let's say, array element 0 and array element 1. And I'll copy into here my swap function. Okay, so let's start marching through this. So first thing we'll do is we'll initialize this array with 9, 2, 1, 7, and 3. And then we'll call swap. So here's our new stack frame. We got swap, we got A, B, and temp. And when I click on next, we'll see that A gets the value 9, which was array element 0. B gets the value 2, which is array element 1. And now we're doing the swap. So 9 goes into temp. That's what we expect. And now the 2 gets copied over to A. And then B gets the value that was inside of temp. So we can see that the values of A and B have indeed been swapped. It used to be 9 and 2. Now it's 2 and 9. But then when we come back to main, we can see that nothing has been changed in this array. So the way to fix this so that the swap function doesn't just get a copy of the values to be swapped, but actually gets the values themselves to be swapped, is to change the syntax a little bit. And I'm going to just show you what change you need to make, and then we'll explain what it means. So the first thing we need to do is modify the way that swap is declared. I'm going to put a star in front of both A and B. And then inside of the swap function itself, I'm going to put a star in front of A and B. And then finally, when I call swap, I'm going to put an ampersand in front of the two values that I want to swap. So now let's visualize the execution and we'll see what's going on. So we're going to initialize the array just like we did before, 92173. We're going to call swap, but then we're going to see something different here. We're going to see that A and B don't get copies of 9 and 2. What they get instead are pointers. They're not actually, the value of A is not 9, and the value of B is not 2. What A is now it's pointing to the 9. You can kind of see it there. It's pointing to the 9, and B is pointing to the 2. I think that looks a little better if I make those straight. So when I start clicking through next, we'll see that temp gets the value 9. So now what temp does is it gets the value that A is pointing to. That's what this star here means. The star in front of the A here means get the value that A is pointing to. And then what this line here, what line 5 means is take the value that B is pointing to and copy it into the thing that A is pointing to. So what B is pointing to is the number 2, and what A is pointing to was the number 9. And this statement, line 5, says take the 2 that B was pointing to and put it into the place that A was pointing to, which was where the 9 was. And then finally we move to line 6, which says take the value that's inside of temp, which is 9, and move it into, that's what the equal sign means. The equal sign does not actually, like in C, does not actually mean make these two things equal. It means copy the thing from the right-hand side into the thing that's on the left-hand side. So copy the value that's inside of temp into the thing that B is pointing to. So if I click on next, we'll see that the 9 went into the thing that B is pointing to. And now swap is done. And we can see that those two elements in the array, the 2 and the 9, have been reversed. Now, I can do this with like any two numbers. They don't have to be array elements. I could do something like int x equals 5 and int y equals 10. And then I could say swap and then ampersand x. Remember, the ampersand just goes in front of the thing that you want to swap. And then ampersand y. And notice I didn't change my swap function at all. I only changed main here. So x and y get the values 5 and 10. Then we're going to call swap. And it's a little hard to see here. Let's see if we can make those arrows be a little easier to see. There we go. So A is pointing to the number 5, and B is pointing to the number 10. The value of temp is going to be whatever A was pointing to, which is 5. And now it's going to copy the thing that B was pointing to into the thing that A was pointing to. And then finally copy the thing that's inside of temp into the thing that B is pointing to. And now the 5 and 10 have been reversed. They've been swapped. Okay, so what's going on here? What's all the stuff with here with this stars and ampersands and other stars? So there's basically 3 things you need to know about pointers. One is, how do you declare them? How do you create a variable whose type is a pointer? Right, before now, we've seen variables of type int. We've seen variables of type float and double and char. But now we've got a new variable type called a pointer type. The next one would be, how would you, let's say, send a pointer? Or another way to put that would be, how do you create a pointer out of an existing variable? And finally, how do you use one? So let's go over these. First of all, how do you declare a pointer? What you do is you put a star in front of your variable name. Putting a star in front of a variable name tells you, or tells the compiler, that this is not going to be just an ordinary variable, it's going to be a pointer. So when we say something like int star a, what this says is a is going to be a pointer to an integer. And if we said, let's say, float pointer b, this means that b is a pointer to a float. And we'll talk a little bit more about what does it mean to be a pointer, right? We'll get into that in just a moment here, but this is how you interpret this declaration. That if you see a star in front of a variable name, it means that that variable is not the thing itself, but is a pointer to that thing. So a is not an integer, it's a pointer to an integer. And b is not a float, it's a pointer to a float. So what that means is that somewhere out there, there is a float. Let's say its value is 3.5. And b is not like associated with that float. It's not directly associated with it. It is sitting off somewhere else. And b points to that float. So there's really kind of like two values here, two boxes. There's the box that holds the float itself. And then there's the box that's associated with b. And b doesn't contain a float. It contains a pointer to, a reference to the float. It's kind of like, what would be a good analogy? Like you've got a person. And a person has a name, but a person also has a phone number, a cell phone number. And so you have another person, right, who also has a name. But if that second person wants to reach out and contact the first person, all they have to know is that person's phone number. And then they're able now to basically, to stretch the analogy, like access the other person, be able to talk to them, be able to communicate with them, be able to get information from them. So that second person is not the first person. It's actually a separate entity. And that second person has the first person's phone number. And when you have that person's phone number, you're now able to like get information from them, give them information, right? So you can copy information to them, and you can pull information out of them. So that's what this picture is representing. Is we've got two things here. We've got b, and we've got the actual float itself. Now notice that this float itself doesn't necessarily have to have a name. It's just out there somewhere. Just like your cell phone, right? All you need is someone's phone number. You don't necessarily need to know what their name is in order to be able to call them. All you have to do is type in their phone number, and then you can reach them. Now, the other person might have a name, and then you could contact them by their name, but if you have their phone number, you can contact them as well. Okay, so when you declare a variable, declare a pointer, you just put a star in front of it. So this applies only to variable declarations. If you want to declare a variable, declare a pointer, you just put a star in front. So here's one of the confusing things about C, and I wish they hadn't done this, is the star gets used in at least 3 different ways in the language. Obviously, it's used for multiplication. We've seen that before. It gets used in pointer declarations, and it also gets used as pointer use, which we'll get into that third bullet point. So it gets used 3 different ways. 2 of them are kind of related to each other. They have to do with pointers, but their use is a little bit different. For the second bullet point, the way you create a pointer out of an existing variable is to put an ampersand in front of it. And we saw that in our program that we wrote with a swap. When we want to take an existing value, like x, and then send into the swap function not the value of x, but a pointer to x, we put the ampersand in front of it. Basically, it kind of like does a cast, right? It takes an existing variable and it converts it into a pointer temporarily. And then finally, to use a pointer, which is also called dereference, which in a third way to say is like to go to the thing that the pointer is pointing to. Is to use, again, the star in front of a pointer. Okay, so to declare a variable, to declare a pointer, you put a star in front of the variable name, and that says that this variable doesn't contain the actual thing itself, but contains a pointer to that thing. To create a pointer, that is to take an existing variable and make a pointer out of it, put the ampersand in front, and then finally to dereference a pointer, to take a pointer, to take the reference of something and go to that thing, you use the star. So these two here look very, very similar, but this star up in the top is only used for declarations, like with a type out in front, and this star over here is only used for dereferencing, like inside of an expression or inside of a statement. So let's go back and look over here. This star here on line 4, star A, is that a declaration or is that a dereference? And how can you tell? So on line 4, we see star A. Is that a dereference or a declaration? That is a dereference because it's inside of a statement. It's actually inside of an expression. How about on line 1, the star A up there? Is that a declaration or a dereference? So that one up there is a declaration. And we know it's a declaration because there's a type sitting out in front. That's how the compiler knows. If it sees a variable name and then it looks in front of it and sees a type, then it goes, ah, that's a declaration. You're creating a variable here. If it does not see a type in front of it, then it goes, oh, that is a use of a variable. That is going and fetching its value. Okay, and then down here on line 13, we see the ampersand in front of x, and that tells us take the thing that x is and create a pointer out of it. So it doesn't modify the value of x. All it does is it temporarily turns not x into a pointer, but creates a pointer to x, and then passes that into swap. All right, so I know it's a little confusing at first, and again, I wish C hadn't used the star in 2 different ways here that have to do with pointers, and then plus the third way that has to do with multiplication. But I guess they just sort of ran out of symbols on the keyboard. Pretty much every symbol on the keyboard is used somewhere in the C language, And so maybe they just decided they didn't have any more that they could use. So they had to, no, actually this is not entirely true. The star and the ampersand historically come from, I believe it's the assembly language that the original Unix computer, which was a PDP-6, I think, back in the 1960s and 1970s. That one used the star and the ampersand for the same purposes in assembly language, to be able to take a register or a memory location that contained the address of something and then go to that address. Or to calculate the address of something. So if you have a variable sitting in a memory location somewhere, then you can get its address by using the ampersand. And so the people that made C just used that same syntax, carried it over. So I guess that kind of like brings up the next topic, which is like, what's going on with all this pointer stuff. So let's take a declaration like int x equals 5. It's both a declaration and an assignment. And int y equals 10. And let's dig a little deeper into what's going on inside the computer. So when the computer analyzes these two statements, it builds something called a symbol table. And a symbol table has two pieces of information in it. It has the name of a variable, and it also contains where that variable lives in memory. And this is probably one of the most important things that you need to understand about computers, is that everything lives somewhere in the computer's memory. And the computer's memory is really just an array of boxes. Each one of those boxes has an address, and the addresses are sequentially numbered, starting at 0 and going all the way up to whatever the maximum size of your computer's memory is. And you can put values inside those boxes. Really, all you can do is put numbers inside of them, but you can treat those numbers as characters, or you can treat them as strings, or you can treat them as images, but really there's just a whole bunch of numbers. So we can say that x and y live in a couple of memory locations, and when you declare two variables in statements that are adjacent to each other, the computer most likely is going to put those two variables next to each other in computer's memory. Now, it doesn't really matter where they actually go in the computer's memory, but conceptually they probably are right next to each other. That's just the easiest thing to do. So let's say these two boxes up here represent two memory locations in the computer's memory. Let's say one of them lives at memory location 5000, just to use a easy number. So in this symbol table, the compiler will set up x to live in memory location number 5000. So it stores that information in the symbol table so that it has a quick and easy reference to it, that if it needs to find out where x lives in memory, it just looks in box number 5000. And really, when your program gets compiled and turns into assembly language and ultimately turns into the machine language, the names of the variables are gone and replaced with memory locations. So nowhere in the assembly language will you actually see the value or the word x. What you'll see is a memory location, and the compiler has set up ahead of time where x is going to live in memory. And then y. Let's say y is going to go, and I'm just going to no, I'm not going to do that. Let's say y is going to go right next to where x is. What would be the address of y? So x lives at memory location 5000. Where does y live? Well, the way to figure that out is you need to know how big x is. How many memory locations does x actually take up? Now, on most systems, an integer is a 4-bit, not a 4-bit, a 4-byte or 32-bit quantity on most, and it is on ours. So if x takes up 4 bytes, that means y must live at 5,000 plus 4, or 5004. So where these variables are laid out in memory has a lot to do with how much space each one takes up. Characters only take up 1 byte. Shorts take up 2 bytes. Integers take up 4 bytes. Longs take up 8 bytes. Floats, I think, take up 4 bytes, and doubles take up 8. But it's all system dependent. It's going to be different on different processors. But on our processor, an integer takes up 4 bytes. So we know that y lives at memory location 5004. So inside of our main, we then called swap. And then our swap was declared like this: void swap int pointer a, comma, int pointer b, we had a declaration of a variable called temp, and then it was temp equals star a equals star b, and then star b equals temp. So the swap function itself also has a symbol table. And there's 3 variables in here. One of them is called temp. And what do you think the other 2 variables are called? What are the names of the other 2 variables? You'd think they would be called like pointer A and pointer B, but they're actually just called A and B. The names of the variables are A and B. So we got a variable called A and a variable called B. The type of A is not integer, it's pointer to integer. And the type of B is pointer to integer. Okay, so this is the type sitting out in front. This is the variable name. This is the type. This is the variable name. There's a question here. Are local variables stored in contiguous memory rather than at random locations? Typically, yes, just because it's easy. Remember, local variables are stored in the stack, and the stack is growing, well, realistically, the stack is growing downwards, but you can think of it as growing upwards. And then you just basically stack those variables on top of each other, which means they're going to be, at contiguous memory locations. What you don't have control over is the exact ordering of them. So is temp going to go first, then x, then y? Or is it going to be y, then x, then temp? Is it going to be x, temp, y? You don't have any control over that. The compiler gets to decide how to arrange them. And oftentimes it is told to you that maybe they are at random locations, but that's because you shouldn't depend upon them being in contiguous locations. You shouldn't rely on that fact. So yeah, typically they are in contiguous locations, but they don't have to be. Okay, so just like before, there is a symbol table for swap. There's 3 variables in it. And let's say swap's memory locations start at 6,000. So let's say address A lives at 6,000. Where's B going to live? Where is B going to live? What address is B? A is 6,000. What's B? Well, the exact value is going to depend upon what system you're on. And I see a lot of people are asking 6004. In our particular system, that is not correct. It's not 6004. What you have to know is how big is a pointer. Remember, the type of A is a pointer to an integer. So you have to know how big a pointer is. And our system is a 64-bit system, so addresses are 64 bits, which is 8 bytes. And that means that B is going to live 8 bytes later than A. At 6008. Okay? And then where does temp live? $6,012. Very good. So 8 bytes. Is that right? No, not 6,012. That would be 6,016. Right? 8 bytes further than B. So A takes up a total of 8 bytes. B takes up a total of 8 bytes. Temp only takes up 4 bytes, but it has to live 8 bytes later than where B lives. Okay, so let's analyze what's going on here. So we create a variable. We create a variable called x whose value is 5. And so that means we're going to put the number 5 inside of the memory location starting at 5,000. And then we move on to the next statement, which is put the value 10 into y. So the symbol table is consulted. The value of, or the address of y is 5004. So the computer says, take the value 10 and put it into memory location 5004. And then call swap. Okay, so what is this? What is this ampersand x? Now, if we normally would just put x there, what the computer is going to do is it's going to consult the symbol table. It's going to say, okay, tell me where x lives. Right? So x lives at 5,000. It's going to go to memory location 5,000, pick up the number 5, and then that's what's going to go here. Now remember, that's only if this is x. And then if y is sitting here, it's going to consult the symbol table, find out that y lives in 5004. It's going to go over the 5004, pick up the 10, and that becomes what goes here. So this becomes a 5, this becomes a 10, and that's what goes into swap. Okay, that's what would happen if it was just x and y here. But we have the ampersands in front of them. Remember what the ampersand means. The ampersand means convert this into a pointer. So we're not going to go fetch the value of x. What we're going to fetch instead is where x lives. So this ampersand x here, we consult the symbol table, and we go, oh, x lives at 5,000. That's what goes here. Ampersand y. We consult the symbol table. We see that y lives at 5004, so that's what goes here. So we're not passing in the values 5 and 10 into swap. We're essentially passing in the values 5,000 and 5004. Okay?
May I interject?
Yes.
So this seems like a lot like pass by reference.
Yes, it does seem like pass by reference. And this is the way that C basically simulates pass by reference. We're passing in a reference or a pointer to where that variable actually lives. I don't want to cloud things too much at this point, because people who study programming languages and design programming language would say that this is not true pass by reference. This is a simulation of it.
Okay.
It's as close as C is going to get to pass by reference. But you can think of it as I'm passing a reference in. You're right. I'm passing a pointer in. But where things get cloudy is I'm passing in the value of a pointer. So it's still passed by value, but the value I'm passing in is an address rather than the number itself.
Okay.
A true pass by reference would pass in like a reference to the variable, but you wouldn't be dealing with addresses. It's kind of fuzzy in there. C++ supports real pass by reference, and C doesn't. Like in C++, you can declare a function to get a reference to x and a reference to y, which is different from getting the address of x and the address of y. And then the caller doesn't have to know that that happened. So the caller just says, call swap with x and y, and they will get reversed. They will get swapped. Because the way the function is declared, it says, I'm going to get a reference to x and a reference to y, and then internally it can do the reversing, the swapping. So in true pass by reference, the caller doesn't necessarily know that's what's happening. But in C, the caller does know, because the caller has to explicitly put in these ampersands.
Ampersands and the stars at the declaration of the function, right?
Yeah. The way you do it in C++ is you would go int ampersand
The
A.
ampersand right there, yeah.
Yeah. And that says, give me a reference. And so the caller doesn't have to know that happened. The caller just
So
says,
would it be a syntax error if you passed a value into the void swap that wasn't a pointer?
yes.
Ah, okay. That's yeah.
Yeah.
Thank you.
The compiler will catch that. Okay, does that answer your question?
Absolutely.
Good. Okay, so we're calling swap, and we're passing in essentially the value 5000 and 5004. So that's essentially what takes the place of this ampersand x. The ampersand x takes on the value 5000, and the ampersand y takes on the value 5004. So we're essentially calling swap with those two numbers. So that means the 5000 goes into A and the 5004 goes into B. So let's start filling in this diagram over here. So we've got a variable called temp. What goes into A? How are we going to fill in these three boxes over here? Now remember, A essentially is this first box, and B is essentially the second box, and temp is this third box. So what do you think goes inside of this first box where A lives? Remember, 5000 is being passed in here, 5004 is being passed in here.
Would it be the memory locations, the 5000 and 5004?
Yeah. So sitting inside of box 6000 is 5000. And sitting inside of box 6008 is 5004. Okay, why is that? Because A is not an integer. A is a pointer to an integer, which means A contains not the number 5 or the number 10, but it contains a memory location. In this case, 5004. 5,000. And B is also a pointer to an integer, so it contains a memory location. The actual value of B is a memory location. Here it's 5004. All right, so now we're on this statement here. Temp equals star A. So what happens is, anytime you see an equal sign inside of a statement, anytime you see an equal, an assignment here, the way the compiler or the way the computer executes this is it evaluates the right-hand side. And this is literally called the RHS, the right-hand side. And this is the LHS, the left-hand side. The right-hand side is evaluated first. And then whatever value is computed is then copied over to the left-hand side. So the equal sign here doesn't mean make these two things equal to each other. It means, literally, copy the right-hand side over to the left-hand side. If you've taken the assembly language class, the assignment operator turns into the move instruction, which just copies values from one memory location into another memory location, or one memory location into another register. Okay, so what does this statement do? So the star A here means, okay, first of all, consult the symbol table, figure out where A lives, go to that memory location, and fetch the value there. So remember, the value of A is 5,000. And then the star in front of that means, okay, now that you have a memory location, go to that memory location and see what's there. Okay, so the value of A is 5,000. The star in front means go to memory location 5,000 and pluck out the value you see there. Okay, so we wander over to 5,000. Here it is. We see the value 5. And so that's what value this is. Okay, the value of A is 6,000. No, sorry, the value of A is 5,000. And the thing that 5,000 is pointing to is the number 5. So we've evaluated the right-hand side, and now we copy that over to the left-hand side. So it says copy the number 5 into temp, right? And we know that temp lives at 6016, so we put the number 5 there. All right, already you can see in this diagram we've got a mixture of kinds of values in here. We've got some values which are addresses and some values which are integers. All right, I know I'm plodding through this really slowly, but I want you to think in terms of two things. One is this diagram that I'm drawing, and two, the fact that variables live somewhere, and the values contained in those locations could be either just numbers or they could be addresses, depending upon how that variable is declared. All right, we got 2 more statements to do, so we're almost done. All right, so next one. Right-hand side first. First thing it's going to do is going to look up the value of B. What's the value of B? The value of B is not 6008. What is the value of B?
5004.
5004, right. So remember, B just lives at address 6008, but its actual value stored there is 5004. So this here is 5004. And then we dereference it. So the star in front of the variable name means apply this dereferencing operation to the thing that comes right after it. So B is 5004, and then the dereference here says, oops, that was wrong, 5004, and the star in front of that 5004 essentially means go to memory location 5004 and see what's there. So the computer goes up to 5004 and it sees that the number 10 is sitting there. So the value of this whole thing is 10. And then we do the move instruction. Move the number 10 into star A. So that says move the number 10 into whatever A is pointing to. So A's value is 5,000. Move the number 10 into memory location 5,000. So that's going to have the effect of taking this 5 and replacing it with the number 10. And then finally, the last statement, star B equals temp. So I'm going to take the value of temp, which is 5, and we're going to move that into whatever B is pointing to. So B, its value is 5004, and we're going to move the number 5 into memory location 5004. So that's going to have the effect of replacing this 10 with a 5. And now those two values have been swapped. And this works because swap is not past the numbers 5 and 10, but is past the addresses where the 5 and 10 live. Now, I think some of you may have one question, which is like for this statement and this statement here, why didn't we just say B equals temp? Or why didn't we just say A equals star B, right? Because that would seem to make sense, right? I want to take the value of B and dereference it, right? So find the thing that B is pointing to and go fetch that value, and then just put it into where A is. So two things wrong with this. One is I don't want to actually take the number 10 and put it where put it over the value of A, because A basically is the number 6,000. I don't want to replace that with the number 10. Because that's now like not an address, right? It's just a number. And likewise for this one here, I don't want to take the value 5 and just replace the value of B, or replace this with the number 5, replace this with the number 10. I don't want to do that, right? Because A and B contain addresses, and this is just copying a number into them. And the other reason why this doesn't work is it has to do with the types. Let me move this up over here. Does this work? And if you remember the diagram I drew last week before, I have equals, we have A over here, and then the way these operators go is there's the star and then the B. So the B is evaluated first, then the star, then the A, then the equals. What's the type of B? The type of B is int pointer. So then we move up the tree and we apply the star operator to an int pointer. And what the star operator does is it basically removes one layer of the pointerness, right? So if B was an integer pointer, then applying the star operator to an integer pointer just turns it into an integer. Then we turn our attention to the left-hand side. What's the type of A? Well, A is also an integer pointer. So now what we're saying is copy an integer into an integer pointer. And that's not going to work. It's a type mismatch. The types on both sides of the equal sign have to be compatible with each other, and you can't copy an integer into an integer pointer. One's an address and one's a number. Now I know internally everything's just a number, right? But the compiler is going to prevent you from doing stupid things like this. The compiler is going to say you can't copy an integer over an address. It just won't allow it. So this will not work. So let's go back and look at our program here. And you know what I'm going to do is, let's see, let's go back into our functions here. Yeah, right here. Actually, no, what I'm going to do is I'm going to make a new file. There's just too much stuff here. Let's just call this swap.c. I'm essentially going to take this code over here and just make a little program out of it. And then after I do the swap, let's print out. So before I do the swap and after I do the swap, let's print out the values. So x equals %d, y is equal to %d. And then we'll do the same thing after the swap. Okay, so we can see x and y are 5 and 10, and then afterwards they're 10 and 5. So that's what we wanted. Okay, so right after we print out the values of x and y, let's also print out their addresses. And the way you print out an address is you can use %p as a placeholder. And I can find out where x and y live. I can get their addresses by just putting an ampersand in front of them. So here are the actual addresses where x and y live. And on my diagram over here, I just said it was like 5,000 and 5,004 and 6,000, but the actual addresses are these. These are hexadecimal addresses. They're 64-bit quantities represented as hexadecimal digits. And we can see that the addresses are actually pretty large, right? They're big numbers. And if you remember, I had this diagram. With those segments in it. And there was the text segment, the data segment, and the stack segment. And the text segment was down here at low addresses, and the stack segment was up here at high addresses. And so we can see from those numbers that the addresses are actually fairly large. They're not in like the 4, 5, 6-digit range. They're up in the, dozen-digit range, right? Which means that we can infer from that these x's and y's are living up in high memory. So they're actually up in that stack segment. We can see also that most of the digits of these addresses are the same. But just like the last 1 or 2 digits are different. So let's ignore the stuff that's the same and look at just the stuff that's different. So essentially, x lives at, and we'll ignore all this stuff here, just look at the last 2. X lives at, actually let's look at the last 4, 79AC. And y lives at 79A8. So numerically, which of these 2 numbers comes first? So if I was to place these in numeric order, would x come first or would y come first?
Y.
Looks like y comes first. So here's 79A8, which is where y lives. And here's 79AC, which is where x lives. And the other question is what's the difference between these 2 values here? What's the, like, are they 4 apart? Are they 2 apart? Are they 8 apart? How far apart are they?
Seems like they're 5 apart, but
No, they're not 5. Let's count here. So the way you count in hexadecimal is, you go 0, 1, 2, 3, 4, 5, 6, 7, 8. There's our 8. And then we go 9, A, B, C.
4.
So
Right, I
they're
did
4
0,
apart.
10.
So there are 4 bytes different between X and Y, which is exactly what we expected, right? If they're laid out in contiguous memory, we would expect them to be 4 bytes apart from each other because they're integers and they're 4-byte quantities each. So the interesting thing is that Y comes first and then X. And actually, that makes a lot of sense to me. And let me see if I can explain it to you. Remember, the stack grows downward in memory. It starts here at high memory and it goes downward. So as you put things onto the stack, the memory locations are going to decrease. So in our program, we declared X first and then Y, which means on the stack, X goes above Y. And if we were to create more variables, they would start going below those as well. They would start building downward. And that's really because the compiler just like assigns a memory location to these variables as it encounters them. So it sees the declaration for X first, and it assigns a memory location to it, and it sees the value of Y, and it goes, oh, I'll just put that in the very next memory locations downward. So I'll subtract 4 from the memory location, and that's where Y will go. And the next one's going to go 4 memory locations below that one, right? So it's just going to build itself downward. It's just really just, like I said, just assigning memory locations as it encounters the declarations. Okay, so the memory locations we can see are decreasing because the stack is growing downwards. And then let's look inside of swap. Remember, swap has actually has 3 variables. So inside of swap, let's put printf temp address %p, a address %p, and b address %p. And then we'll put address of temp, address of A, and address of B. In fact, that's how I remember what these symbols are. Mnemonically, I think of, like, I want to get the address of something, so I'm going to put the ampersand or the and symbol in front of it. So I'm getting the and address of something. That's how I remember it. I'm getting the and address of something. All right, so what do we got here? So, also we can see that because the program is running again, it's a different run, the memory locations are slightly different. So gosh, now I need to change my diagram over here just so it matches this picture. All right, so X lives at 8C4C, and Y lives at 8. Oh, no, I had that wrong. BC4C, BC4C, and BC48, which again is 4 bytes difference, so it's exactly what we'd expect. And then here inside of swap, we have temp, A, and B. Temp lives at BC0C. A lives at BC18. And B lives at BC10. I'm just copying values right off the screen here. So let's put these into numeric order. Which of these comes first? Well, let's see. Let's put them in order. BC0C is actually the first one. And then BC10 is the next one, and BC18 is the last one. So it goes temp BA. And again, if you look at the way the program is written, the way the variables are declared, A comes first, then B, then temp, just simply going from top to bottom, left to right. So it would make sense in our diagram that A would be all the way to the right, and then B would be to the left of that, and then temp would be to the left of that, because remember, the addresses are going down. The addresses in this diagram, this is the lower addresses, and this is the higher addresses as we count going to the right. And so what that means is that in my stack, if we look at all 5 of these addresses in total, we can see that temp is the lowest one, followed by B, followed by A. So here's temp, here's B, then A. And then above that, numerically, is Y and then X. But there's a little gap. There's a gap in between Y and A. We can see that here the locations are like, in the teens, and here they're in the 40s. So there's a bit of a gap in between A and B. Not A and B, A and Y. So it's kind of like these are moved down. But nevertheless, we have this one large stack, and then within within the larger stack, there's like 2 smaller, and I'm kind of addressing a question that came up, kind of like 2 smaller stacks. But really, it's one large stack. So this is main up here, and this is swap. And they just get, these stack frames just get piled on top of each other. But remember, the stack goes downward, so they're going downward, but that's what's going on. So every time we call a function, we build a new stack frame, put it below the one before it, and then just put the variables within it. Okay, so every time you call a function, you get a new stack frame, and that stack frame contains the local variables for that particular function. So here we've got 2 functions, one called main, one called swap. Main gets called first, so it goes up at the topmost addresses, and it builds the variables down from there. And then swap gets called, and so it gets a new stack frame, and then it builds its variables down there. And there's a little bit of a gap here because there's some housekeeping that has to go on. There's some additional values that have to be loaded onto the stack in order to make the stack work correctly. That's what accounts for that little gap there. So really, everything is contiguous. It's just that there's some values pushed onto the stack that I'm not showing to you. Okay. Does that leave you with any questions? I'm sure it does. I'm sure it leaves you with a ton of questions, but like, what do you have for me? And I can see if I can answer them. Anything? Nothing at all? Really? Maybe you're just, I don't know, your brains are probably full at this point. Well, why don't we do this? Why don't we take a break? And when we come back, I'll go over the assignments for this week. I know you're working on other stuff as well. So there's really only, for this week, there's only 2 warm-ups to do. And then next week, we'll introduce the level up assignment. So don't worry about the level up for this week. We're not ready for it yet. There's just 2 warm-ups to do. We'll go over that when we come back from the break. Okay, so let's take about 10 minutes. Let your brains digest a bit, and then we'll come back.
Recording stopped.
Okay, that's just for the Zoom recording. YouTube is still going. Let me see if I can scroll back and look at some questions here. Do I stream from home or a campus office? I am at home. Wondering if the cat I've heard in previous videos will make an appearance. Let's see, is she here? She is not here. I don't know where the cats are right now. But yes, she occasionally sleeps under my desk. But she's not here right now. She's probably sitting at the food dish, waiting for food to magically appear. I know what I want to do during our break here. I want your subjective opinion on something. This has nothing to do with computer science. This has to do with streaming. I got a new microphone. Actually, I have 3 microphones now. And I want your opinion about which one you think sounds the best. Of course, you don't really know what my voice actually sounds like because it's all influenced by acoustics in the room and the microphone I'm using and how much I'm amplifying them. And so what I want your opinion is I'm gonna try all 3 microphones. And I want your opinion about which one you think sounds the best, right? Again, you don't know what I actually sound like. And I do want to clarify one thing, that the way the human ear works, if someone asks you, does sound A or sound B sound the best to you, typically you'll pick the one that's the loudest, right? If something is louder, it's perceived to be better than one that's quieter. And so I want you to be aware of that, because when I try on a different microphone, it might be a little bit louder, it might be a little bit quieter than the one you heard previously. I want you to try to say I'm not going to listen to the loudness of it, I'm going to listen to the quality of it. All right, so I'm gonna mute my current microphone. So I'm going to mute my current microphone and then put on a different one, and then we'll see what it sounds like. Ooh, that is quite a bit louder. Let me quiet that down. Wow, that is very different. All right. That microphone picks up a lot more room noise. I can hear it in my headphones, that there's a lot more room noise with this one. But what do you think? So the other one is what's called a cardioid microphone. So it basically only picks up sound coming from above. This one is an omnidirectional microphone, so it picks up sound from everywhere, including below. And you're right, this one sounds louder because it's picking up more of that room noise. But what do you think about the quality of the sound? Is it better? Yeah, everyone's saying it's louder but carries more noise. I did not expect that at all. This particular microphone comes, fairly well recommended, and I can see it would be useful for environments where, it's quieter around, or you do want more of that kind of like ambient sound. But is that ambient sound is that a good thing or is that not a good thing? Wow, it does pick up a lot more room noise. I'm picking up my third microphone, and you can hear me shuffling around with the stuff on my desk, whereas the other microphone doesn't pick that up because it really only picks up stuff from above. But you think the sound is good. And then, yeah, that's the nice thing about an omnidirectional is if I turn my head to the side, it doesn't get quieter because it can pick up sound from everywhere. And I actually do have an omnidirectional microphone of the same manufacturer of the first one I was wearing. So that might be another one to try. Okay, let me swap a third microphone in. And I'm not going to influence you with name brands yet. So that, won't say oh, I recognize that brand, that one's better. All right, let me mute the microphone and put this one in. All right, now, whoa, that one's a lot quieter, isn't it? Let me boost the gain on here. So what do you think about this one? So this one does not pick up as much of the room noise either. Yeah, the first one could be useful where you have multiple persons participating with a single microphone, so it could pick up the voices of both people. You like the first one, and you like it because of the quiet sound. It makes the class sound more serious. All right, so what do you think about this one? So this is microphone number 3. So this one, I think, is also an omnidirectional, but it doesn't seem to pick up as much of the room noise. And as such, it may sound quieter because you're not, I'm playing with things on my desk, and you can hear it in the microphone, but it's not nearly as noticeable as it was with microphone number 2. This one seems to have the good audio of the last microphone, but without the extra noise. Good to know. Hold on, I'm going to duck out for just a moment, and here, I have actually microphone number 4 in one of these bins. Is it in this one? Yeah. The problem with microphones is, there are, of course, companies that sell studio microphones and microphones for bands and such, but they're usually not returnable. Once you buy a microphone, that's it. It's yours. If you don't like it, tough. And I think the reason why they're not returnable is because, typically with a handheld microphone, you're talking into it, and that means you're spitting into it, and they don't want to sell a microphone that someone else has been using. Okay, so I'm going to put on microphone number 4. Tell me what you think. Okay, so this is microphone number 4. This one picks up a lot of the room noise too, but it's not like as hissy, I think. And again, I'm just going based upon what I'm hearing in my earphones. I had to quiet that one down a bit so it doesn't distort too much. So this is microphone number 4. What do you think about this one? Is the neighbor out hammering like the last time? Yes, you might have heard it just about a few minutes ago. You could hear the power hammer going. All right, so let me switch back. Microphone number 1. And this is the first microphone that I used. Wow, that one's a lot quieter. I gotta boost that up. How's that? That's better? Okay, so this is the first microphone, the one that I was using for the last hour or so. This is microphone number 1. What do you think about that one? So this one does not pick up nearly as much of the desk sounds. So you can't necessarily hear my typing. You can't hear me picking up stuff as much. But it means that also if I turn my head a little bit, the voice seems to kind of come and go a bit. So opinions. Now, it's hard for me to switch all the microphones back and forth. We've got, you think this one is the best, microphone number 1. Is that because it just isolates the voice better? Other people say they like 3 or 4 over 1. So you like pretty much all the others over this one. Don't hear as much background noise with number 1. That's absolutely true. You like number 1. Okay, so the microphone I'm wearing right now, I can unclip it, but it makes a little bit of noise when I do that, is this one. This is the Shure 185 cardioid microphone. It's rather big. Here's its twin brother. It's rather big, and the reason why I've been using it this semester, but I hadn't been using it in previous semesters just because it's heavy. I mean, it's physically big, and when you clip it onto your shirt, it tends to try to tug down on the shirt. So I've had to wear sturdier shirts this semester. But I think because it's physically bigger, it's got a bigger diaphragm inside, and it tends to pick up stuff better, right? A better reproduction of the voice. So this is the omnidirectional version of what I'm wearing right now. What I'm wearing right now is called the cardioid. So it has a pickup pattern that just focuses on stuff that's right above it. This one here picks up more of the stuff that's all around it. This was microphone number 4, the one I'm holding here. The one I'm wearing currently was microphone number 1. And people are saying they kind of like number 1 because it doesn't pick up as much of that room noise. And then microphone number 2 was this one. This is one I just got because it came recommended on many YouTube videos. It's by a relatively new company called Deity. And this one is tiny. Let me compare it to the one that I was just holding up a moment ago. Right, here's the Shure microphone, and here's the Deity one. You can see it's huge. I mean, it's like comparatively, it's just microscopic microphone. So this one would be great if you want to really conceal it. You know, you want to maybe put it behind a button, or you can even put it in someone's hair so that, you know, it's just peeking out below their hairline. But this was microphone number 2, and this was the one that picked up a lot of the room noise. But it's an omnidirectional, so it picks up noise from everywhere. But it also seemed to be like more like tinny or hissy, right? It picked up a lot of the noise, and it really was sensitive to like things like crinkling noises and tapping noises. This one is about $125 on Amazon. The Shure ones are also about $125. They're all kind of in the same ballpark range of prices. And then microphone number 3 was one you actually can't get anymore. This is an Audio-Technica microphone, and it's a size-wise, it's in between the Deity and the Shure. It's kind of a mid-size one. This was one that I was wearing in. If you've watched my videos from earlier in the year, like back in the spring or before that, this is the one I was wearing. And so people said, like, it sounds pretty good. Sounds okay. I decided to try the Shure this semester because I think when I listen to my voice, I like the sound of the Shures better because it seems to pick up this. But I know what I sound like, right? I know what I'm supposed to sound like, and so I listen to the Shures and go, oh, that's more like what I actually perceive myself as sounding like. But really, what matters is what you think. You don't know what I actually sound like. All you can go by is what the microphone is picking up and whether you like it or not. And that's really ultimately the difference between a lot of microphones is, does it work for your particular voice? You know, you listen to personalities on the radio or on podcasts, and again, you don't know what they actually sound like, but they're probably using microphones that they like or that their listeners like and say that seems to work well with your voice. Like, you know, as far as I'm turning my head all the way around so you can't hear me as well. Where is my... Somewhere around here I have a box with more microphones in it. But it has decided to hide. Oh, here it is. Now this is a really nice microphone, but this is not one you can wear. This is a desktop microphone, and this is when you speak into the front end of it, not the side, the front end of it. Then this one makes your voice sound like $1 million. I mean, it's just amazing what this one does. This is a $300 microphone, $350, somewhere in there. A lot of podcasters like that particular one, so I really like what it sounds like. But it's too big to use. I mean, I could like have like a, some people like, if you watch Twitch videos or podcast videos, some people like the look of the arm sticking down on the side of the screen with a microphone in it, and some people don't. And I personally, for my videos, prefer not having the microphone sticking in the picture. There was a time when I did these videos and I actually had the microphone just out of view, right below the camera view. But the problem with that is that it blocks my view of my screen, right? So I kind of have to like look around it a little bit. And so although I sounded really great, and if you look at some of my videos from like, I'm trying to think how long ago, like maybe 6-7 years ago, the ones where I'm doing the green screen thing was just my head down in the corner. Those were done with this microphone. Oh, I just realized that you're looking at my iPad this whole time. You're not looking at my face. But hopefully you can see my face up in the corner. What type of connectors do all the microphones use? So these are like professional quality microphones, which means they're actually feeding into a radio pack that I wear on my belt. And then there's a receiver on my desk. And then that radio pack, or the receiver, has an XLR connector, the big fat connector with the 3 holes or the 3 pins in it. And then that goes into my audio mixer where it mixes in the music and the sound from other people on Zoom. And that is a USB connector coming out of it going into my computer. So the connector on these microphones is just this like mini XLR connector. So like a little miniature one. And that goes into the transmitter on my belt. And then the receiver has a full-size XLR going into the mixer. And then that has a USB coming out going into the computer. I mean, you can get microphones like what I'm wearing that have just USB connectors, so it can go straight into a computer. But I wanted to send it into a mixer first. And then I can do things like adjust the tonal quality and mix it in with other audio sounds. And okay, so break time is long over. Am I planning on doing any C++ tutorials? No, sadly. I don't know C++ as well as I know C. I just never really got into it. Actually, let me start my recordings again.
Recording in progress.
So the question came up, do I do C++ stuff? And the answer is no, because one, I don't teach a C++ class. We do at our institution have a C++ class, but it's another guy who teaches it. I just never really got into C++ myself. C++ came out in the late 1980s, early 90s. And the university that I was at started using C++ in a couple of the courses. And, you know, having been a C programmer already by that time for a couple of years, I didn't see the point. I was like, why all this extra stuff when we can get by just fine with arrays and structs and pointers? And so, because they weren't, object-oriented programming had kind of like just come out and no one really knew what to do with it. It's like, hey, we got object orientation, but you can treat it kind of like as regular programming without objects, but with all the object stuff thrown on top of it. So we just didn't get it. We were just like, what? This is like, it's got this weird C syntax, and it seemed like just a bunch of extra stuff. And at that time, the programs ran slower than C programs did because of the extra object overhead. So I just never got into it. I would say, knowing what I know now, 30 years later, I'd probably get into it more. Because back then, C++ was taught as C with extra stuff on top of it. And to some degree, that's true. You can take a C program and compile it on a C++ compiler, and it should more or less work okay. But nowadays, if you really want to learn like C++ the real way, you wouldn't introduce it as C with extra stuff. You would introduce it as its own language. And really, that's what the textbooks would now say. C++ and C have diverged to the point where C++ and C are now distinct languages. Sure, they share a lot of syntax in common, but so do a lot of other languages. But they're really just distinct languages at this point. And so I think it might be easier to teach C++ if you don't make reference to C. And you don't say, hey, this is the way C does it, and so this is the way C++ does it. You just do it, you know, as its own standalone language. Now, that being said, I still think there are a lot of dumb things that are done in C++. Like the whole like C in, C out. I get C in and C out, right? But the whole like arrow thing pointing, in place of like printf or something. I think when that was first introduced way back in the 80s, we saw that. We students like saw that and went, well, that's cool, but why would you do that? Like why would you overload those operators and make them do something else? It just kind of like clutters up the meaning of what's going on. I mean, we can see like, the value of x is going into C out, right? We can see the arrow thing. Like it's kind of cute, but that's pretty much the only place in the entire language where that's used. It's like they were just showing off. They were just like the C designer was just saying like, hey, we can do this, so why not do it? This is something you can do. You can overload operators, and like I said, you're just showing off that you can do that. It doesn't. It's the only place where that's done. No one else ever does that in C++ to like redirect a variable. You don't use that to like copy the value of x into y. You don't go like x arrow y to copy the value. You use equals, right? So, I mean, it's great that you can overload operators, but don't do it for the sake of overloading an operator, just so that you can show off you can do it. So I think that there's some dumb stuff going on there. I do like the C++ standard library with the built-in data types. Java basically adopted a lot of them. The templating in C++ looks very similar to the templating in Java, so I think that's great. C++ has the same include file problems that C has, which means you have to not only manage your code, but now manage these include files and these header files. And you basically declare your class structure in one file and the methods in another file, whereas Java just puts them all in the same file, which I think is a vast improvement. So, I mean, C++ has some like vestiges of its C heritage, which could be gotten rid of, but isn't. So, like I said, I never really got into it. I would say learn C++, absolutely. I mean, go ahead and, as a Java developer, go ahead and learn C++. There's no reason not to. The compilers these days are really good. Generate really tight, really fast code. I think people have said like C++ code is like within a couple of % of the equivalent C code. Really good code generation. Because they share the same backend. They share the same optimizers and stuff. So I don't see any reason not to learn C++, but once you have it in your toolbox, take it. Now you have two things in your toolbox, and you're probably able to make an informed decision about whether or not it's the right tool for you. Me, I'm just making a knee-jerk reaction, like, oh, I didn't like it back 30 years ago, I still don't like it. That's not a good reason to say you don't like something. Okay, let's take a look at the 2 warm-up assignments. And I know some of you on YouTube have been asking, how can you get a hold of these assignments? And that's something I'm working on, but I need to be able to put them in a place where you can like get access to them. I do actually have a Bitbucket repository, and I got to go find the address again, that has some of the assignments in it, but not all of them. And it's really only some of the later ones. So it's something I need to work on in my copious free time, is to make these available somewhere for you. Okay, so 2 warm-up assignments. One is very similar to the fill array we were doing a week or 2 ago, but this one's going to use pointers. So same size array as last time, still a 40-element array. You're still going to fill in the values 0 through 9, the elements 0 through 9 with the values 0 through 9. So the same values are going into the array, the exact same values, just that you're doing it differently. So now instead of one giant main with the different loops to fill in the array, you're going to have functions to do that. You're going to have a main where the array is declared, and then it just calls the other functions. a function to fill in elements 0 through 9. You can use the array syntax with brackets to access the elements of the array. So you use the same array calling syntax that we've been studying up to this point. Fill elements 10 through 19 with the values 100 through 190. You can either use the array syntax or you can use pointer arithmetic. We're going to get into pointer arithmetic next time. So you could do it the bracket way now and then change it over to the other style next time. Fill elements 20 to 25. Use pointer arithmetic. Again, we'll get into that next time. I'm totally thrown off this semester by the fact that we had a holiday last Monday. Was it last Monday or the Monday before that? So everything now is like off by one day. Well, off by half a week. So normally this lecture would have been done on Monday and we would have today, Wednesday, to talk about pointer arithmetic and the assignment. So I'm kind of like having to push things forward and push things back a little bit. So array elements 26 through 39, use the bracket syntax or pointer arithmetic. And then you'll need a next callouts function, the same one you had in the previous assignment. And you also need a print array function. Okay, and all those functions should use loops except for the function that fills in elements 20 to 25. Each of the filling functions should be passed in the array as a pointer. And then use the pointer syntax in the function declarations. Oh, and we'll get into that next time, right? But again, it's just a warm-up problem. We're just getting used to the idea of passing functions into, or passing arrays into functions, and then accessing those array elements within the functions. And then warm-up number 2. Wow, my internet is slow today. Oh, because I didn't plug in my cable. That's why. Let me go and get one of those adapters. Better reach into my bag and pull one out. Oh, I went into such a rant yesterday about USB connectors. You had to be there. It was in my classroom. Oh, where are they? Oh, here they are. Is this one? Will this work? No, that will not work. I can do the same rant today. I can replicate my rant. Oh, I guess I'll have to use this other one. Sorry, folks. The problem is that my bag is like a dark color, and all these adapters are also dark colors, so I can't see anything in there. Everything is just dark gray. Oh. Website's under heavy load. Maybe it's not the fact that I'm not plugged in. Let's try it again. Here we go. Okay, so in this one here, we're going to input 3 floats, just 3 numbers, exactly 3 numbers, and then you're going to sort them into order and then print them out. That's it. So you have a main, a get prices, and a swap function. So get prices should prompt the user to type in all 3 numbers, and remember, it's just exactly 3 numbers, so actually no array in this at all, just 3 floats. And then it's going to put them in the correct order. So the user types in, let's say, 6.2, 3.95, and 4.15. By the time get prices is done, it has put them into the correct order from least to greatest. So main just calls get prices. Get prices is going to sort them. And then get prices will then, main will then print out the 3 numbers. And then get prices is going to call swap. Now, since there's exactly 3 numbers, you only have to call swap 3 times. You can basically check, you can, like if we have 1.65 and 4.25 and 3.14. What you can do is, let's say this is A, B, and C. You can look at A and B and see if they are in the correct order. And if they are, just leave them. And if they're not, call swap and reverse them. And then you can look at B and C and see if they're in the correct order. And if they're not, you can swap them. And then finally, you can do one more comparison. I think that's A and B again, and see if they're now in the correct order or not. And if not, swap them. So you can call swap 3 times, exactly 3 times. No, at most 3 times. And that'll get this 3 values in order. So we're not doing a full sort with an array of 20 elements. We're doing exactly 3, A, B, and C. You can call swap up to 3 times, and then that'll put them in the correct order. So again, we're just getting the idea of passing pointers into functions and getting values back from them. Nothing fancy at this point. So main is going to declare 3 floats. It's going to call get prices, passing in pointers to the 3 float variables, and then it's going to print out those 3 floats. And then get prices is going to prompt the user to enter those 3, and then it's going to go through what I just talked about, the technique for getting those into order. And then when get prices returns, those 3 values are now in the correct order. So that's it. That's it for the warm-up problems. So next time, we will talk about pointer arithmetic, and we'll also introduce this new assignment, the CSI assignment, Computer Science Investigations, in which you are going to look for and extract images off of an SD card. So the setup for it is basically I took some pictures with an SD card, and then when I popped that SD card into my computer, it says this card is corrupted. There's nothing there. And so we're going to write a program to pull the images off of that SD card. And you have to do it by scanning through the contents of the SD card, treating it as an array of bytes, and looking for JPEG images. And I'll show you a way to detect when you found a JPEG image. And then when you find that image, you're then going to tell your program, okay, save the bytes from starting here up to here, and then it'll create a file that contains just that JPEG image. And then you can view it on your screen and see if you've actually got the image. So that's what we'll do next time. But for now, we're just playing around with arrays and passing values in and out of functions. Okay? So that's all I had for you today. Are you left with any questions?
I have one quick question about pointers.
Yeah.
So pointers are a data type. So can you return a pointer from a function?
Absolutely.
Wow. Okay.
Yeah.
That's trippy.
So this is leading up to something that we couldn't do before. What we couldn't do before was, this is just one example, create an array inside of a function and then pass that back to the caller. And a use for that would be, let's say you're writing a program to have the user input the prices of stuff that they ate at a restaurant. Well, you don't know how many things they ate. So you might ask the user, how many things did you eat? And then create an array that holds just that number. So if you prompt them to say, how many things you eat? And they say 4, then you're going to create an array with 4 elements in it. And if you want to create that array within that function that, prompts the user for how many things they ate, you can't pass that back because then the array ceases to exist. It's a local variable within that function. So what you want to be able to do is create an array in a part of memory that won't disappear, and then pass back the address of where that array lives. So you'll pass back a pointer to that array. And we'll get into that next week.
Awesome.
Yeah, so basically, a function to that like that would be, let's bring up my screen here. So normally what you try to do is, let's call this like a get list, something like that. So prompt user for length of list. And then you could do like float prices length. And then you want to do something like, say, return prices, which is an array of floats. But you can't, because this array is a local variable to get list. So it's not going to work. You'll get a warning or an error from the compiler that says you're trying to access an array or return an array that was created within the function. So you can't do this. But if you could, then you would say float array, get list, so it returns an array. Or another way to say it is float pointer. And what you're returning is the address of where that array lives in memory. So you're returning a pointer. Regardless of whether you're returning the array or you're returning a float pointer, you're still, in both cases, returning the address of where that array lives. So
Right.
yes, functions can return pointers. And we will use that a lot throughout the semester. So that actually comes up in the CSI assignment. You're going to load in this file, this huge file that contains all these JPEG images, and you're going to get back a pointer to where the contents of that SD card lives in memory. So, long answer to your question.
But thorough.
Any others? Okay, well, why don't we wrap it up for today? We'll be back on Monday, and I'm going to try to promise no more like canceled classes. I told the people that I had the meeting for on Monday, I said, yeah, I can't cancel my classes, so that's the last time we're going to do that. They said, okay. We'll do it on different days. All right, folks, have a good one. For those of you living in our area, it's good to have some rain. Finally, it's not 115 degrees anymore. It's actually raining a little bit today. It rained yesterday, rained over the weekend, which is great for the fire, right? And I actually had some students write to me and say that they were displaced by the fire, that they had to be evacuated, and that's why they haven't got their assignments in. And I said, don't worry about it, right? It's more important to take care of your family and your home. But I said also, I wish I had known. I wish you had contacted me earlier, because our college has resources available for when these sorts of things happen. That they can put you in touch with financial aid, and they can put you in touch with resources to make sure that you've got food and you've got shelter and you've got just whatever you need to be able to get through these emergencies like this. And there is a kind of a bucket of money available to help you out. So if you find yourself in that kind of situation where it can be even as simple as like, I'm out of gas and I don't have money to put gas in my car this week, we can put you in touch with assistance to make sure that those things get covered. I have done that for some students. I've had students, I've had the college help out with rent assistance, to help out buying textbooks, to help out with technology things like my laptop broke this week. Is there one that I can borrow at least for a week? Yes, we can put you in touch with those resources. So if those sorts of things happen to you, please contact me, in some way, and I will put you in touch with people that can help you out. That's a really, really great thing that our college does, is just make sure that basic needs are taken care of so that you can focus on your studies. We got a question. Oh, rather than copying content, should we point to it? That's a really good question. Is now that we know about pointers, is it better to just point to things rather than copying them? And it really, there's no like recipe answer there. It really depends on what you want to do. One of the purposes of copying values into functions is to isolate them, so that if that function modifies the value, when you pass a value into a function, into those variables that are in the function declaration, they become local variables within that function. And so the function can modify those values without affecting the caller, because the caller has passed in a copy and retains its own copy. So it serves as kind of like a firewall between these two functions. If one function calls another function and copies the values over, then the second function could modify those values without affecting the first one. And that there could be reasons for doing that. Like you want to, let's say one of the values you pass in is the length of something, or the number of items or something. And so that the function that gets called could use that variable as its counter variable. Like if you pass in the value 10 for the length of something you want to do 10 times, the function could actually use that number 10 and just count down to 0. And that would have the effect of doing something 10 times. So it's modifying that variable, but it doesn't affect the caller. Now that we know about pointers, you might ask, well, why don't I just pass pointers into things? Why don't I pass these values in as pointers? There's a couple reasons why you might not want to do that. Now, by giving the function that you call a pointer, you now have also handed over access to the variable that's being pointed to. So if main calls a function, and main has a variable called x that has a value, and passes in a pointer to x, now that function has the ability to modify the value of x. So that firewall now has a hole poked through it, and the function can basically get access to the variable that came from the caller. So if that is your intention, you want the function to be able to modify the value of the variable, then yeah, you would pass in a pointer. But if you don't want it to modify it, you want to make sure that does not happen, you wouldn't pass in a pointer. And the other reason to pass by a pointer is to reduce the amount of data being copied. If you have an array, and the array has 10,000 elements in it, you probably would not want to pass in a copy of the array. It would take a long time to copy that entire array. And in fact, C does not directly support any such thing. There's no way to just pass in a copy of the array. The language will not make the copy for you. You would have to make the copy yourself and then pass that thing in. And so really the only way to pass in anything larger than a primitive type, so anything other than an integer or a character or a float or a double, is to pass on a pointer to it. And that just reduces the amount of data that has to be copied around. If you want to pass in an array, you're just going to pass in the address of the array. That's just 8 bytes rather than 80,000 bytes. If you want to pass in a complex data structure like a tree or a hash map, then you would pass in a pointer to it rather than a copy of it. But that comes with its downsides. Now the function that has been called now has access to it and can change it. So there's nothing the language itself does not prevent the called function from doing that once it has a pointer to something. So you just kind of have to trust that the called function is not going to modify something. And Java really actually is the same way. If you pass a primitive type into a method, it will pass in a copy of that primitive type. If you pass in an object type into a method, it will just pass in the address. in order to save the amount of stuff it has to copy. And so that's where pointers occur in Java. Anytime you refer to an object, you're actually using its address. Anytime you refer to a primitive type, ints, floats, doubles, characters, bytes, booleans, you're just using the actual values and you're passing in copies. Okay? So, yeah, there's good reasons not to pass in pointers if you don't want that function to get access to the data itself. Maybe that function was written by a third party and you don't trust that third party to not modify the values, then you'd pass in a copy if you could. But for anything larger than a primitive type, you're probably just going to pass in the address because it just reduces the amount of data you have to copy. Now there are other languages out there. I'm trying to think of ones in particular. The functional languages like the Scheme and Lisp and ML and some of those. When you pass in an array or you pass in a data structure, you actually pass in a copy. So it makes a copy for you and then passes that in. I mean that's clouding things up a little bit. What does it actually do? It passes in a pointer, right? Because it's easy to pass in a pointer. It's just 8 bytes to copy. But then if the function itself tries to modify the data structure, then internally it'll start making a copy. So it makes a copy on demand. So if you pass in an array into a function and you're telling it, I'm not passing in the address of the array, I'm just passing the whole array. What it'll do is it'll actually pass in the pointer, but then if that function starts modifying the array, it'll start copying the elements of the array over so that internally that function is not modifying the caller's array. It's modifying its own copy of it. Oh yeah. So like C# uses a ref keyword to be explicit about are you passing in a copy or you're passing in a reference. Java doesn't have this ref keyword that I'm aware of, unless it's a really recent language feature. If we assign one pointer to another, what's going to happen? Well, you'll end up copying the addresses. And the compiler will enforce that the addresses have to be compatible with each other. So if one pointer is a pointer to a float and another one is a pointer to an integer, you cannot just directly copy one to the other. The compiler would say one's an integer pointer and one's a float pointer, and although they are both addresses, they're not compatible with each other because they point to different kinds of things. But you can take an integer pointer and copy it to another integer pointer. So the types have to match just like they did before, right? When you use an assignment operator, the type on the left-hand side has to be the same as the type on the right-hand side. So if the types are different, even though they're both pointers, but if they're pointing to different kinds of things, it won't allow it. And part of that's just to make sure you as the programmer don't do stupid things like mix up pointers that are pointing to different kinds of things. And also it has to do with, there's a technical reason for that, and that is when you have the address of something, you need to know how big that thing is, so you know how many values to look at in the computer's memory. So if you pass in an integer pointer, the thing that's using that pointer has to know to look at 4 bytes of memory. And it knows that because it knows what type of thing that pointer is pointing to. And if you pass in a double pointer, it's still just an address, but the thing that's using that pointer has to know now to look at 8 bytes of information to grab that entire double value. So that's why the types are important, is because although they are just addresses, the function using that address has to know how many bytes of memory to look at to fetch the value that's being pointed to. So, long answer for your question. Anything else? I guess my question is, did you understand what I just said about that, the number of bytes? So like if I have an int pointer A. A points to the starting address of this 4-byte quantity. And if I have a double pointer B, B is also a pointer. It's just an address, and it points to the first address of this double, but the double occupies 8 bytes. So although they're both pointers, the one using the pointer has to know how much memory should I look at in order to fetch the entire value. And that's why it's important to keep the types correct. So that's what I was referring to. Okay, so like I said, I think that's going to be it for today. We'll come back on next week on Monday, and we'll go over pointer arithmetic and more about passing pointers into functions using a slightly different syntax, and also start going over that CSI assignment, which is going to be a lot of fun, right? It's going and finding those JPEGs out of that file is something that's kind of open-ended. I kind of give you some hints, but really the actual technique that you use is going to be up to you. So I would suggest, like, get started on it as soon as you can, and then if you're watching the live session on Wednesday, we'll be able to answer any questions you have about it. And then we might also get a chance to answer questions about it the following Monday as you work more and more on the assignment and have some questions about how it's supposed to work. Okay. Yep, have a nice day, everyone. And it looks like a lot of you on YouTube were here because you saw my Makefile video. So a lot of people end up on my channel because of that one video I made many, many years ago. But I guess it's still useful. So I say you're welcome for that video. So take care, everyone. Have a great weekend. And I will see you next time. Bye-bye.
Record.
Oh, Lord Melbury, you're here. Hello from the UK, and we got some people from, I saw it earlier. Got some people from, scrolling up. Oh, I missed it. Someone said where they were from. It was like Turkey or something like that. I don't see it anymore. Anyway, glad to have you here. And I'm glad that you find these videos to be useful. Vietnam. Good to see you. Yoshi, good to see you. How many people are here? About 5 or 6? We got about 6 people here. We'll keep watching. Next time we'll do more pointer stuff. We'll be doing pointers for the rest of the semester, but we'll get more into pointers. I'll show you more about what's going on under the hood. I started drawing some diagrams today. I'll draw more diagrams next time, really kind of showing you what's going on with those stack frames as it builds the stack frames downward and then unrolls them as it returns from functions. So we'll go over more of that, and that will help us understand the assembly code that's being generated. We can look at we can write a program, generate the assembly code, and then look at the assembly code and see what's going on. But in order to be able to do that, we have to understand a little bit about how stack frames are constructed. And once we learn that, we can then look at that assembly code and go, that's what's going on. I can see the local variables being created. I can see them being destroyed. I can see values being put into them. And it also addresses one question that you might have, which is, well, every time the program runs, it runs in a slightly different part of memory. How does the compiler know ahead of time what the memory addresses are going to be? I show you that symbol table, and I show you the numbers that appear there. But that symbol table is actually built at runtime, not at compile time. So how does the compiler know what to do in that case? So we'll answer that question. Hello from Germany, or hello to Germany. Good to see you here. Cameroon. Oh, you're in Germany now, but originally from Cameroon. I think it's interesting. A lot of people are watching me. I get very few people watching me from the United States. Most people are from other parts of the world. Well, it's time to take off. So thank you for participating in my microphone audition. And it looks like we're sticking with the one that I've originally been using, the one I've been using this entire semester, which is the Shure 185 cardioid microphone, the one that's kind of large and pulls down on my shirt a little bit, but everyone seems to think that that one sounds pretty good. And it also isolates the sounds from around the room and around my desk pretty well, so you can't hear me playing with stuff as much as the other microphones could pick that up. All right, so oh, and you're from Brazil, Yoshi. Well, I hope to see you on future streams. So wave hello next time I come on, which will be on Monday. Maybe it's Tuesday for you. What's runtime? So runtime is the environment that gets set up when the program is running, which differs from compile time, the environment that gets set up when the program is being compiled. So there's certain things that the computer can infer about your program when it's compiling it, and there's certain things that it can't tell and it won't know until the program is actually running. And those are things like, what address is the program actually living at the moment it's running? So it can tell things about scope and the names of variables when it's compiling the program, but it can't tell exactly what address that they will be at until it's running, until it's actually running. Did I say that correctly? Scope, names of variables at compile time. I don't think I said that correctly. So at compile time. But it won't know until the program is actually running when it actually discovers what the memory locations actually are. So that's what runtime is. And also runtime involves things like the shared libraries, the C standard library and the math library. Those get linked in at runtime. They are learned about at compile time, but they actually get linked in at runtime, which means that you can do things like bring in a new version of the C standard library as a system update, and then all programs get that new version the next time they're run. If they were linked in at compile time, then your program would be stuck with the version that it was compiled with forever until you recompiled it. So runtime environments are important to learn about. And you might not get that kind of information until you've taken a programming languages course or a compiler construction course and really get the difference between a runtime environment and a compile time environment. But I'll start introducing it now, and then hopefully you can get more understanding of it as you move through your courses. I was telling one of my students yesterday in another one of my classes, I was kind of introducing this idea that there's more to computer science than just writing programs to do stuff. Right? You can write a program to make a game, or you can write a program to make an app on your phone, but that's really just one sector, one piece of computer science as a discipline. There's all this other stuff about things like hardware and software and the dividing line between hardware and software that actually is very fuzzy. It's not a hard line between those two things. And the fact that you can like implement or emulate a computer system inside of another computer system, that one can emulate another one. The thing that brought this up was someone mentioned someone had built an entire computer out of Minecraft blocks. And I said, yeah, you can do that. You can actually build a computer inside of Minecraft, which is running inside of another computer. You know, it runs slower and slower, but at least it works. And he said, and the next step after that would be to build a computer inside of that computer. So you got a computer running inside of a computer, running inside of Minecraft, which is running inside of a computer. And I said, once you like learn about that, and you learn about all this like abstract stuff that's part of computer science, it's like it's amazing, and it's just you know, your mind just goes. It was small before, and now it's it's huge, and you realize that there's way much more to it than just writing apps and writing websites. And I think that's just fantastically interesting, as that boundary between what we can do and what we know is possible is expanding as technology moves forward and we're able to do more and more things. What is it that runs the run engine? It's not really a runtime engine in the sense of like a game engine. It's just that there's certain pieces of information that are knowable at when you compile the program, and there's certain pieces of information that are knowable when you run the program. And there's a distinct separation between the two of them. That there are some things that you can't know at compile time, and there are some things that you can't know at runtime. You know, here would be an example. And this is an abstract example, not a concrete example. An abstract example would be, how long is it going to take a program to run? And let's just divide it between like short, like less than a second, and long, more than a second. Like obviously, if I actually just ran the program, I could measure how long it takes, right? I could, start a timer, and I could run the program, and if it takes less than a second, I could say, whoa, it took less than a second. If it takes more than a second, I could say, oh, it takes more than a second, right? But let's say you have a program that takes a really long time to run. Let's say the program takes a year to run. How would you be able to write a program that could measure how long that program would take and give you an answer? Like obviously, I could just watch the program, and I could write a program that watches another program and then tells me how long it took to run. But how could I write a program that could predict that? Like without actually running the program, could I write another program that would predict how long it would take another program to run without actually running it? So could I analyze the program's source code and make a determination from that? Like this program will run quickly, or this program will take a long time to run. And could I write a program that could analyze the source code of another program and come up with that answer quickly? So it could give me the answer in less than a second. So it could look at the source code for another program and answer the question, program X will run in less than a second, or program Y will take more than a second to run. Okay, so that program, let's call it A, could that program work in such a way that it could get the answer in less than a second? That's the difference between runtime and compile time. Runtime is like how long the program actually takes to run. And compile time is what can we learn about the program without actually running it. And this is one of the questions that is actually, and this is an interesting question, this is one of the questions in computer science that has no answer yet. The question is, can we write a program that can analyze the source code for another program and determine how long it's going to take that program to run? Short or long, let's say. Let's just break it down into that. Because here's where the twist comes. So we have this program that can analyze another program. But let's say the source code that we're feeding into it is really long. Would that program then take a long time to compute the answer to whether the first program would take a long time or not? So would we then need another program, a third program, that can analyze whether the second program took a long time or a short time? And you can see how these could stack up very easily, right? We have a program that either takes a long time or a short time. And we have another program that looks at that one and determines whether it takes a long time or a short time. And then we have another program that could look at that one and determine whether that one takes a long time or a short time. And then we can just keep going with that. And where does it stop? Does it ever stop? Can we ever write a program that could say for sure another program is going to run short or long without actually running the program? And it turns out the answer is no. We can't write a program like that. I'm diverging way into theoretical computer science, but basically this is one of the unanswerable questions in computer science is, can we write a program that can analyze another program and answer the question, will it take a long time or short time to run it? And the reason is because we can't itself write a program that can analyze the second program to determine whether it takes a long time or a short time. And it just keeps stacking up from there. There's no end to that chain where you can write a program that could tell you in a short amount of time whether another program will take a long time or a short time to run. And that leads to another question is, can we write a universal debugger? Can we write a program that can find bugs in other programs? And the answer is no, we can't. Because of that first question. We can't answer the question, will the program take a long time to run or will it end quickly? And that means that we can't find bugs that cause programs to run for a long time when they should have taken a short time to run. So that means there's a class of computer bugs out there that we can never detect. Which means there are programs out there that we can never write. And once you get your head around that, you're just like, wow, there's like the stuff that we know is possible, and then there's the stuff that we know is impossible. And for all the power of computers, for all the speed, for all the processing power, there's this line that we can't cross with any computer that we know of. That's amazing. I think that's just amazing. So, hopefully, if you go on and take more courses in computer science, you'll learn that. Take a course in theoretical computer science. There are actually some of those free online courses you can take in which they dive into those types of questions, and it doesn't cost anything. And you can watch the lectures and you can participate in some of the programming assignments, and you can learn about some of those questions in computer science that are just mind-blowing. And once you get it, you just realize that programming, writing programs and apps is just a small portion of this huge discipline. And like I said, I think it's just incredible. Anyway, I'll leave you with that. So I hope you have a good day. If it's nighttime for you, hope you get some sleep, and then we'll be back next week. So have a great day, everyone. Take care. Think about what I just said. Go look it up. And goodbye.